Thanks a lot for watching this video. The idea of this video is to show how to generate an implicit geometry with Altair tools and how to mesh it in 3D to perform explicit simulation. So in the first step, I will give a brief introduction to what implicit geometry is. Then I will show how to generate such implicit geometries with Altair Inspire. In a third step, I will demonstrate how to transfer this geometry to HyperMesh in order to use the meshing tools that exist in HyperMesh to generate a 3D mesh of a unit cell of a lattice structure. And then I will show how to propagate this unit cell mesh to represent several cells in different directions and to have a more representative use case of a real lattice structure. So what is implicit geometry? Implicit geometry is described by equations that impose conditions on the points that belong to the geometry. It is different from classical explicit geometry, where we usually provide the direct coordinates of the points that describe the geometry. It allows to use simpler equations to represent more complex shapes. It is very useful in the case of lattice structures, as you can see on the left-hand side of the presentation. So we will focus on representing such use case that you can see in the videos here, where we want to represent some different lattice structures of different sizes and different complexities. So we want to represent these structures with 3D hexa elements in order to perform the best explicit simulations. And to do so, we need to have clean and precise geometries to rely on to build our mesh. So within Altair Inspire, you have this implicit modeling tab here, in which you can create a primitive, which will be the area in which you want to create your implicit geometry. So let's stick with a standard cuboid of 10 centimeters length. And once you've created this primitive, you can fill it with different kinds of implicit geometries. So let's take, for example, a surface implicit geometry here. So you have a lot of different kinds of implicit geometries. So we can have a look at this Schwarzschild scheme, for example. You can have some kind of empty filling within it. And then you have additional options here, which are interesting on the sizing part of the menu. So you can specify the density, which will more or less specify the ratio of filling of your implicit geometry for this particular geometry here. You can also specify a field to have a variable density in different directions. So for example, if you create a field that is aligned with the z-axis here, you can see that the density of your implicit geometry will vary with along with the z-axis. And you can specify the minimum and maximum density. So for example, if you don't want a zero density, you can start with a density of 20 and get up to a density of 75, for example, or maybe 50, just to have something more representative. So you can see here that the density of your structure evolves along with the z-axis. So if we just cancel everything, that was just to show this feature. You can also define the number of cells you want per direction. So here we have a uniform spread of number of cells, and you can specify only one cell if you want to represent only one, or you can specify different values along each direction. So for example, 1 in one direction and 4 in the other direction. So if you have the same number everywhere, it should give something like this. And then you can modify the number of cells per direction. So let's stick with a uniform structure and with only one cell, just to show how to mesh it and how to convert it into a geometry that can be used in HyperMesh. So once I've created my unit cell, I can just validate everything. And then what I'm switching back to the geometry tab here, I can right-click on my implicit geometry and ask to convert it to a triangle mesh here, and I can specify the size of the mesh I want to have. So let's say a 0.2 size of mesh. I'm clicking on convert, and then it's going to convert this implicit geometry into a mesh. So the mesh will be a tetra mesh that is only a surface mesh. So I will have no elements inside inside of the structure, but I have all the skins of the geometry that are meshed with triangle mesh, right? So the advantage of this is that I can use the mesh in any finite element solver, and I can also export this mesh to use it with HyperMesh. Whereas the implicit geometry is specific to Altair Inspire, and you will not be able to use it to launch a finite element simulation, a regular finite element simulation, and you will not be able also to import it in HyperMesh. So let's save this implicit geometry as an stmod file. So implicit geometry, stmod, it's going to save it, and I can then open HyperMesh. So what is saved in the stmod file is only the tetra mesh that I've generated in Inspire. As I said, you cannot transfer the implicit geometry from Inspire to HyperMesh. So we can now import our stmod file in HyperMesh, and you can see here that the only thing that is imported is the mesh. You have no geometry. So you have a surfacing tetra mesh exported from Inspire in this stmod file. You can either base a 3D mesh on this surfacing tetra mesh, or you can regenerate the geometry in HyperMesh from this surfacing mesh in order to generate a cleaner hexa 3D mesh, for example, if you want to perform crash explicit simulations. So to do that, we can get into the 2D menu here and generate surfaces from finite elements, right? So we can select sources. So by pressing the Alt button, I can select elements by face. So I need to right-click, I need to right-click select by face first. And then by pressing the Alt button, I can select elements by face directly. So I will select the 6 circular faces first to generate these surfaces. And then I will generate the 2 remaining ones, which take a little bit longer to be generated because they are a bit more complex than the circular ones. Now you can see that I have faces. Okay, so I will step out of this tool and I will delete the initial tetra surfacing elements because I'm going to modify the surfaces. And when I modify the surfaces, by default, the mesh that is associated to these surfaces will be also updated when the surfaces are updated. So I don't want this to slow down my process, so I will select all the elements and delete them, and I don't need them anymore because now I'm going to generate some quad elements. So now I need to stitch these surfaces because you can see that on the red lines, I have no link. My surfaces are not stitched together, and I want them to be stitched. So I will step back into the topology menu here, click on the split stitch button, and I will select the stitch menu, and I will make sure that this optimize surface quality option is selected. That's the best practice to have the best surface quality possible when stitching surfaces. So I will select all my surfaces and ask for them to be stitched, and this will automatically, providing the tolerance I've set up is consistent with the size of the model. Here you see that my tolerance was 1 exponent minus 4. So you can see here that the surfaces have all been stitched and the red lines are now green, which means that the surfaces are correctly stitched together. And here in the preference, I can ask for the scale to be showed every time. And you can see here that I can now see my scale. This can be a good option to be sure the tolerance distance or the maximum stitching distance provided is consistent with the size of the model. So now I have all my surfaces stitched, and I will delete all the lines that I don't need, all the construction lines that are in the middle of my surfaces, because if I keep these lines, my mesh will follow these lines, and I don't want my mesh to follow these lines. I want my mesh to be uniform on all the different surfaces of my geometry. So I will select this suppress option here, select all my surfaces, and ask for deletion of the construction lines. And you can see here that they are all turned into blue, which means that they will not affect the mesh that will be generated on the surfaces. So now that I have theoretically clean surfaces, I can check it is the case by generating a solid. So in the 3D menu and the solid button, I can create a solid by bounding surfaces. So if all my surfaces define a closed volume, I just need to click on one of them, and all the linked surfaces that define a closed volume will automatically be selected. So that's the case here. I only clicked on one surface and they all turned orange automatically, which means I can create a solid. They define a closed volume. So I now have recreated a geometry, a solid, based on a surfacic tetra mesh that was imported from Altair Inspire. So now that I've recreated my geometry, the idea is to perform a clean 3D hexamesh onto it. To do so, I will split this geometry in 8 different but similar solids based on the easy to identify 3 different symmetry planes that we can see. This is to help the 3D meshing algorithms of HyperMesh to have clean 3D hexamesh. So to do that, I will get into the topology menu here, select the split stitch option, and remain in the split menu here. I can select my solid, and I can now define splitting planes. So as soon as I'm selecting a node here, I will have a menu, a window that pops up to define the symmetry plane I want to use. So let's, for example, stick to the align to a local coordinate system here. And let's say I want this to be stitched to the center of the circular line. So you can see that when I'm moving the origin of the plane, I have these CEN letters that appear, which means that I'm snapped to the center of the circular line that you can see here. This is performed thanks to this button here, where we can select to which kind of entity we can snap our selection to. So as circle center is selected here, we have access to the center of the circular lines to snap to. And here you can see that we have defined our orientation vector of the splitting plane along with the global y-axis. Okay, so we can also click on review to have a cleaner review of how this split is going to look like. And if we're satisfied, we can click play to split our initial solid into 2 different ones. So we can reproduce this step on the 2 created solids and define a plane here and to define this plane, for example, I can press the control button and click on 2 nodes that will define the normal of this plane, but I can also click on these 2 points, for example, to have a different normal vector here. So now that I've defined a new splitting plane, I can move the origin of this plane onto a new location, and I will split my solids with this plane, for example. So now I have only one remaining split to perform, and I want the this split to be like that. So the normal of my splitting plane would be a vector from this node to that one, for example. So I can select all my solids, click on plane, and hold the control button while clicking on the two nodes that define my normal vector of the plane. So if I'm clicking again, here you can see that with these two nodes, they define the normal vector of the splitting plane. And I can now position my plane wherever I want to have cut the split that I'm looking for. So now I have split my initial cell volume in 8 similar solids based on the 3 symmetry planes that I've initially identified. Once I have done that, one way to mesh the full unit cell would be to first check that all these solids are mappable. So I'm clicking on the mappable option here, and as they are displayed in transparent orange, this means they are mappable. So I can come back to the topology display, for example, and I can use in the 3D menu the map tool here to perform the 3D mesh of all the solids in one step. That's the first possibility, right? So I can select all my solids, ask for an auto detection of source and target, and I can specify the mesh size and the type of elements I want to use. So if I want to achieve in the end 8 node hexa elements, I will have to stick to the quads only type to be sure I only have surfacing quads from which I will get 8 node hexas when I extrude them through the thickness, right? So I can check that this element size is relevant compared to the dimensions of my geometry, and I will click on mesh. The first click on mesh will give me a preview of the surfacing mesh that the 3D mesh will rely on. So I can see here that I have some different element densities on all the different lines of my geometry. So I could ask for a similar density everywhere, for example. So I can click on all the lines I want to control. I could then ask for 20 everywhere, for example. Here. Right, so I think I've asked for 20 everywhere. Just to be sure, because my idea is to have a symmetric mesh of my unit cell, so I can replicate it in different directions to have a full structure. Right, so now I'm going to click mesh, and the 3D meshing algorithms will propagate the 3D mesh for the 8 different solids, one after the other. Right, so now that it's done, I can mask the geometry just to have a look at my final mesh. So we have a good quality mesh, but the main drawback of this mesh is that it's not symmetric within the unit cell. So when I'm going to replicate my unit cell in the different directions, I cannot be sure that the mesh of one side will be equivalent, will fall in front of the mesh on the other side. So I would not recommend using this workflow, but I would rather select one of the 8 solids I have created and isolate it to focus on the mesh of one solid, and then replicate the mesh directly. So I will perform the same workflow, but only on one of the 8 solids. I will still ask for the same values here on all the different bounding lines of my geometry. And let's ask for 15, for example, everywhere, just to show how it's modifying the mesh. Right? So now I can click on the mesh button a second time, and here is the 3D mesh of my 1/8 of the solid. Right? Now what I can do is still mask the geometry and perform mirror operations on these different elements. So if you don't have access to mirror, it's because you have several buttons in the same one. Usually you have the move tool that is available by default, so you can click on the small arrow here and ask for mirror. Select your elements and then define the symmetry plane you want to use to propagate this mesh. So let's pick any of the 3 here. So that's the symmetry plane you want to use, and then you can specify where you want to position this plane. So for example, here on one side of my unit cell, I want to keep the original mesh because I want to duplicate it and then mirror it. So I need to check the keep original box here and click on mirror to mirror my mesh. Right? So if I'm looking at the unit cell, that's not the correct direction I want it to do. So I can undo the operation by clicking on Ctrl plus Z and reposition my plane, but in the correct area, for example, here. And I will mirror the mesh in the other direction, which is more consistent with the geometry of my unit cell. So I'm going to reproduce this step to mirror my mesh along the different directions. Here. And the last one, there, along this plane, and positioned here. So now I have meshed my full unit cell, and I'm consistent with the geometry, the initial geometry I had. So now what I can check is the connectivity of my elements. So if I'm picking one of the elements that's been generated and I'm right-clicking to select the attached elements, I can see that I only have 1/8 of the unit cell. So I need to have an additional step to equivalence all these elements together. So I will get into the validate menu here, click on equivalence, select all my elements, and now I need to specify an equivalencing tolerance that is consistent with my geometry. So I can have a quick measure of my mesh size, which is 3 exponent minus 3. So I have very small, we don't even see that these elements are not connected together. So a very small value of tolerance will be enough. Here I can select 5 exponent minus 3 to equivalence all the elements together. And I can see that I have 1500 nodes that were equivalents, which is consistent with my mesh size. And I can now repeat an element, right-click, select attached, or press Ctrl T to see that all my elements are now attached together. So this helps me generating the 3D hexamesh of my unit cell. Now I will see how I can replicate this mesh to represent several cells that are connected together. So I could reproduce the process of mirroring this unit cell in the different directions, but I would have to perform it many times if I have a lot of different cells to be represented. So there's another tool that's called replicate here in the 2D menu that will help me replicate this unit cell as many times as needed in the different directions, only with one step. So I can select all my elements and click on the move button here, and I can replicate this unit cell mesh as many times as I want in any kind of direction. So for example, let's say I want 4 cells in the Z direction here. I can position my tool here in a consistent location. So for example, I can position this tool here. So I'm holding the shift button to select only the move tool instead of moving my elements. And I can position it here, for example, where I can guess that there is a splitting plane here. And I can drag my elements from here to there because I have observed, I have remarked here that this line is coming through the cutting plane. So I have a preview of the replication process, and when I'm clicking on replicate, it's going to effectively generate all the elements and all my different cells. So now I can see that I was sure the mesh would be coincident here because of the mirroring process I've used to mesh my unit cell. Right, so that's the first step in one direction. I can reproduce this step in the 2 other ones. So for example, let's say I want 3 cells in the Y direction, for example. So I'm going to position my moving tool here and drag it from here to there. Have a look at the preview and click replicate. So with the additional steps I'm performing, it's taking longer and longer because there's more and more elements to duplicate, of course. And let's say that the last direction I will only have 2 cells, not to have too big of a model here, so only 1. And this time it will be along the global y-axis here. So let's position it here and move it to there. I'm clicking replicate, and I will have my full structure meshed much faster than if I was using the mirror tool for all these different planes. Right? So I still need to check the connectivity of my elements. So I will I'm pressing the E button to be in the element selection, selecting one of them. And as we saw, I'm pushing Control T, Control button, and T keyboard button to see which elements are attached to the one I've selected. We can see here that they are not all linked together. So I will once again need to get into the validate menu, equivalence, select all my elements. The same tolerance as before should be fine. I will click equivalence, and you can notice here that 12,000 nodes were equivalents. Now I'm exiting the tool, selecting the same element as before. Once again, Control T, and now all my elements are linked together. So I have quite fast generated a 3D hexa mesh of a full lattice structure. I can check if I want by the advanced selection here, the configuration of all the elements I have. So here with the button, I can select elements by configuration, and I can see here that they all have the same configuration. They are all hexa 8 nodes elements. So this is how to efficiently mesh with 3D hexa elements lattice structure.